Let's talk about the center of percussion. And center of gravity is that balancing point, and that's what COG is, center of gravity. We have an axis of rotation. We have some force hitting an object. So you can think of bat and ball if you want, and we'll do that example specifically in a moment. But if something comes in and hits this, that there is going to be at this axis of rotation, which I've labeled as point P, there are forces involved there. And if you hit at the center of percussion, this component that's parallel to the force being applied by an external object, this force right here is going to be 0. So in baseball, if you've played, if you swing the bat and you hit the ball just wrong, your hands hurt, that's because you're not hitting the center of percussion. So let's do an analysis here. That's the Newton's second law. I know F equals ma. And so if I look at the forces in the horizontal direction, or the I hat direction as defined right here, that's equal to ma sub gx. And so that's the acceleration at the center of gravity in the x direction. I've defined j hat to be going up on the page, and so k hat, since it's a right-handed coordinate system, k hat's coming out of the page. So if I look at my torque equation, tau equals I alpha, my torque of F, which is the force coming from the external object, times L sub F, which is the vertical distance from the axis of rotation to where the force is applied, to the horizontal point where the force is applied, is equal to I alpha. And this is I sub P is the moment of inertia of the object as it rotates about the axis of rotation. I know that alpha, relationship between the acceleration at the center of gravity and alpha, is equal to this, L sub G being the distance from the axis of rotation to the center of gravity, the vertical distance. At the center of percussion, this Fpx is 0 as described earlier, and so F, this again, force from the external object, is equal to mass times Ag sub x. Plugging that into this equation right here, we have ma sub gx Lf is equal to IPA over Lg. This a sub gx will cancel out, and what we're left with is the distance from the axis of rotation to where the force is applied is equal to the moment of inertia divided by the mass times the distance from here to here. So we now have a relationship between the distance from an axis of rotation to the center of gravity and to the center of percussion. Let's take a look at specifically of a baseball bat. We're going to treat it as a cylinder rotating about the end cap. Now, technically, usually you've got it choked up and you're holding it more like there. So L sub G would be L over 2. So if it's of length L, so the length of the bat is capital L there. So L sub G is big L over 2. I sub B is 1/3 ml squared. You can look that up or derive it, whichever one you feel like. So L sub F would be, well, plug in the moment of inertia of the bat cylinder rotating about its end, divided by mlg, and you end up with 2/3 L. So the distance from the axis of rotation to where the optimum place to hit it would be basically 2/3 of the way along the bat, typically known in baseball as the sweet spot of the bat. Let's take an example of a gong. Uniform density suspended at the edge, and there's another video where we actually derive the moment of inertia of that, and we find that to be 5/4 mr squared. And so 5/4 mr squared over mr, r being the distance from the axis of rotation to the center of gravity, and we end up with 5/4 r. So the best place to hit the gong so your hands are not vibrating is not in the middle, but just slightly below the middle. And then a pool ball, if you hit it at the center of percussion, the axis of rotation is down here. So that's the point in which you hit the ball and you'll have a perfect rotation. And so plugging into it, we have a solid sphere. That's the 2/5 mr squared plus this, just plugging into the parallel axis theorem, and we end up with 7/5 r. So you would hit, if that distance there is r, you have 1.4 times that distance, so that's written right there. So that would be that optimum place to hit it, so that there's no horizontal force acting on the ball at this point right here. And that's it.